friends. I am Dr. Y.D. Dwivedhi, Professor from Institute of Aeronautical Engineering, Hyderabad. I am in the process of in the course named Aircraft Stability and Control. Today I am going to discuss about these are the topics, and the main topic is aircraft stability derivatives and criteria for longitudinal stability. So in this, first of all, we have to understand that what is the stability. Stability is the process of the aircraft when any external forces are acting, and if these forces are removed, an aircraft tending to come to its original equilibrium condition, then we can say that aircraft is statically stable. In the process of studying the aircraft stability, we have learned in the previous classes that the aircraft from initial onwards, the stability was the basic problem. During the Wright brother also, the Wright brother is the first person who have studied about the aircraft stability and control. You may be surprised that the Wright brothers in their Flyer 1, which they have flown in the Kitty Hawk in 3rd December 1903, they have used the canard configuration. This canard configuration means a forewing which is fitted ahead of the main wing. You can see here that if this is the aircraft, these are the wing and these are the horizontal tail or horizontal stabilizer, but Wright brothers have used here one wing ahead of the main wing, and that wing was named as a canard, and lot of research have been done, and it was found that the canard gives the additional lift coefficient because the lift is acting in the same direction of the wing and the canard. But if you see this tail lift will be in the opposite direction, so net lift of the aircraft will be reduced if we are using the horizontal tail. But if we use a front wing ahead of the main wing, then we can say that the lift generated by the canard is in a positive direction and the lift generated by the wing is also in the positive direction. So net result of this canard and the wing will be in the positive direction. So this type of wing were used by the Wright brothers. But after some time, what happened? People have started using the horizontal tail because this horizontal tail gives a more static stability, especially in longitudinal axis. But the efficiency of this horizontal tail is not as good as the canard, because we know that the aircraft aerodynamic efficiency is L by D. So if the total lift of the aircraft is more, then we can say that that configuration is having more aerodynamic efficiency. So if we use the canard, that canard will give a positive lift. So this positive and this positive, you will get positive. But here what happened in this configuration? Here it will be negative because this angle of this thing is set in such a way that it is supposed to give the lift towards the earth. So it was the concept, and we have to understand that how these things will work. And in this topic, I am going to discuss about this stability derivative and criteria for longitudinal static stability. These topics I am going to discuss today, and hope this will be very useful. So here we have these topics I am going to cover today: stability derivatives, criteria for longitudinal static stability, primary control derivatives, that is called the control power, sign convention of primary control derivatives, example of control moment. Then I will go for right thumb rule for finding positive or the negative moment, then cross control derivative, and followed by references. So we have to go. First topic is stability derivative. You may be remembering in my previous classes that I have discussed about the aircraft stability. In this longitudinal axis, it is called the pitching. If the nose is going up or down, then this process is called the pitching, and this moment is called the pitching moment, M. And if we non-dimensionalize this pitching moment, it is called the coefficient of moment, Cm. So the variation of this coefficient of moment with respect to the angle of attack. And what is the angle of attack? Angle of attack is the angle between the relative wind and the chord of the wing. So if it is flying like this and wing is like this, so this angle from relative wind like this, and so this angle is called the angle of attack. So if we draw the plot between coefficient of moment and angle of attack, then we can say that it is a Cm alpha, dCm by d alpha. And then Cl is coefficient of rolling moment versus beta is side slip angle. So what is the beta? You see, the aircraft is flying like this, and if nose is up, it is alpha, this angle. But if aircraft is flying like this and your wind direction is like this, so from this longitudinal axis to this angle towards the wind direction is called the beta. I am just explaining here. This you can see here that if this is the aircraft, this is the aircraft, it is flying in this direction, but wind is coming from this direction. So this angle, if you see from the top view, this is called the beta, and beta is called the side slip angle. So if you see from the top view, and this is your aircraft direction and this is your wind direction, this is the V infinity and this is the V, and so this is called the beta. So this is called the side slip angle. And here also the rolling moment, the moment which is taking place with respect to the longitudinal axis, so your wing will go up or down. So this is called Cl, coefficient of rolling moment, and the Cn is coefficient of pitching moment. So if the nose is going towards the left or the right, due to this motion there is a yawing moment. This yawing moment is called N. Yawing moment divided by the non-dimensional moment, that is half rho v square, S and C. So this is called the moment. So here we are going to discuss the stability derivatives. These stability derivatives are Cm alpha, CL beta and CN beta, and these are referred as a stability derivatives. They represents the change in applicable moment coefficient with respect to the change in direction of the relative wind alpha for longitudinal motion, beta for lateral and directional motion. The sign of each of these derivative will determine the longitudinal, lateral and directional static stability respectively. So what is the meaning of this here? Sign. If you see here, this derivative, first is Cm alpha. So this Cm alpha means dCm by d alpha. So if we plot a like this is the Cm and this is the alpha. So this sign, if this Cm alpha is negative, so what is the meaning of this Cm alpha negative? It means dCm by d alpha is negative. The slope of this curve, if you see here that this is the alpha, if I draw a line like this, here is positive and here is negative. So the slope of this curve, that is called dCm by d alpha, is negative. If dCm by d alpha is negative, then we can say that it is a statically stable. Okay, so your stability derivatives and their sign are very important, and this sign will say that whether aircraft is stable, it is unstable, or it is neutrally stable. Assume that the dCm by d alpha, which is 0. Okay, then what will happen? Okay, just you see, Cm alpha is equal to 0. It means if I draw a plot, Cm versus alpha, so this plot is parallel to alpha. So here slope is 0. There is no slope. So if like this, then it is a neutral stable. Then neutral static stable. Okay, so the value of, and if it is like this is, so here dCm by d alpha is positive. So if it is positive, it is unstable. So what is it meaning? I will just unstable. So if it is positive, it is unstable, negative is stable, and 0 is neutral stable. This is the 0. I will show you with help of the model. You can see that in aircraft how this thing will happen. Okay, just you can see, I have just now explained dCm by d alpha if it is 0. So aircraft is flying like this and some gust came from here, aircraft nose has gone up, it will remain up. If it is remaining in the same angle after the disturbance, we can say that aircraft is neutral stable. It means dCm by d alpha is equal to 0. There is no variation after disturbance. 0, it means remain constant. dCm by d alpha is equal to 0 means it is a constant. If it is a constant, the same position aircraft will maintain for further time period. Next case is when dCm by d alpha is a negative. Negative means it is a stable. So if it is a stable, then after the disturbance, nose has gone up, but as and when your disturbance is removed, nose will try to come to its original position. That is called, it is a statically stable. Third case is statically unstable. So when aircraft is faced with any gust, the nose of the aircraft is gone up. This increase in nose will make the aircraft further, nose will go up. It will not come down. Means the AC is ahead of the CG. So if the AC of the, just I am explaining with the, this is the wing and this is the AC and this is the CG. So always lift will act at the AC. So if the AC is ahead of the CG, tendency is nose up. This nose up will make the aircraft unstable. The tendency of the aircraft will be unstable. Nose will not come back after disturbance. But in the second case, if you see that this is the AC and if the CG is ahead, okay, then what will happen? This lift force will try and this moment will act in this direction and it is called the minus CM. Anticlockwise. It is a minus and it is a plus. So here, if it is behind the CG, aircraft will be nose down and nose down is dCm by d alpha is negative. The last case and the third case, if you can see here that what will be the position of aircraft CG and AC for the neutral case. This is the wing and if this is the AC and here is the CG also. Both are overlapping each other. Then what will happen? There will not be any moment. Moment will be 0. So Cm is equal to 0. In this case, aircraft will maintain the disturbed condition after removal of the disturbing force also. Okay, so this is the case and in this way we have to understand the. Okay, so next time same thing I am going to explain about the criteria for longitudinal static stability. Just now I have explained about the derivative which is Cm alpha. To have the longitudinal static stability, the Cm alpha should be negative. I told you. So here Cm alpha should be less than 0 or negative. That is the first criteria. So with Cm alpha negative, notice that a gust that causes a perturbation in trim angle of attack to a slight lower value will result in a positive aerodynamic pitching moment. So it is, so perturbation in trim angle of attack to slightly lower value will result in a positive aerodynamic pitching moment, which gives the aircraft an initial tendency to back to the trim condition. Likewise, a gust that causes a perturbed increase in angle of attack will result in a negative pitching moment. Thus, a negative Cm alpha can be seen as a requirement for longitudinal static stability. Okay, so the negative Cm alpha, here if you see in this, the slope of this plot is dCm by d alpha is less than 0 or negative. If this is the condition, then aircraft is statically stable in longitudinal case. And second case, that this Cm naught, it should be positive. This is the 0 and this is the positive direction. So the Cm naught, it should be positive. So these are the two conditions. So dCm by d alpha should be negative and Cm naught, it should be greater than 0 or positive. So to have a longitudinal static stability, the two criteria has to be completed, and these two criteria are dCm by d alpha should be less than 0 or negative and Cm naught should be greater than 0 or positive. If we are able to meet these two conditions, then we can say that aircraft is longitudinally static stable. Now we have to talk about some other derivatives, and these are the Cm delta E, Cmih, Cl delta A and Cn delta R. They are referred as a primary control derivative. So once I talk about the controls, what are the main control? This I will show you here. We have the three main control of the aircraft. One is on the wing. In the wing we have the ailerons. Next is in the horizontal tail. In horizontal tail we have the elevator, and the vertical fin. Here you can see these are the rudder. So we have here R indicate, delta R indicate the variation in rudder angle, delta A indicate variation in aileron, delta E indicate variation in the elevator, and IH indicate the setting angle of horizontal tail. So these parameters we should understand that once I call the Cn delta, Cn means it is a yawing moment coefficient, variation of yawing moment coefficient with the variation of change in rudder deflection. Cm delta E is change in coefficient of pitching moment with the change in the elevator deflection. Cl delta A is a change in coefficient of rolling moment with change in aileron deflection. Cmih is the change in the coefficient of moment with respect to the change in the setting angle of horizontal tail. H indicate for horizontal tail, E indicate for the elevator deflection, A indicate for the aileron, and R indicate for the rudder. I think all the parameters it will be now clear, and what does it mean and how these things are useful. This we are going to discuss in this lecture. So here these all derivatives are also known as the control power, because we have to deflect this, and this deflection will make the attitude of the aircraft to change. For example, Cm delta E is the longitudinal control power. This Cm delta E, the first derivative is called the longitudinal control power or longitudinal control derivatives, that defines the change in coefficient of pitching moment that results from a change in elevator deflection delta E. Same way, Cmih, Cl delta A and Cn delta R can be defined. The higher the absolute value of control derivative, the more moment is generated for a given control deflection. One could think of this as a higher control sensitivity for a given moment of inertia. So higher the absolute value. So this Cm delta E, the value how much you have more, that much more moment is generated. It means that much fast it is acting. If the value of Cm delta E is 5 and Cm delta E is 3. The Cm delta E 5 value is much responsive, much sensitive than the Cm delta E value of 3. So this indicates the sensitivity of the aircraft. Okay, so now we have to see about the sign convention of primary control derivative. So how we have to see that which one is positive and which one is negative. So we can see that the positive elevator deflection delta E is trailing edge down. Just I will explain in this aircraft. Here is the elevator. This you can see the black color. So if the elevator is going down, okay, this is the elevator. If it is going like this, then it is a positive elevator. Positive incidence angle of the horizontal stabilizer IH is leading edge up. So this IH, we can say it is a positive when this leading edge is facing upward. So here it is 0, and if it is going like this, we can say that it is a positive. So IH, incidence angle of the horizontal tail, if nose is upward, we can say that it is like this. So it is a positive. Positive aileron deflection is TED on either aileron, and a composite aileron deflection, that is called the delta A, is defined as the difference between the left aileron deflection and the right aileron deflection. So if you see, this is the aircraft. So left and right, you have to decide with respect to the pilot. Pilot is sitting here. If the pilot is sitting here, the left side of this wing is a left wing and this is the right wing. So if this deflection of the left wing, how much, minus deflection of the right wing divided by 2, it is called the delta A. Okay, so if it is going down, it is a positive, and it is going up, it is a negative. So that formula we have to use. And rudder deflection, delta R trailing is left. So here this you can see, if this leading edge, and if this is going like this, then it is a positive, and if it is going towards the right, it is a negative. So if the rudder trailing edge left, TEL, it is a positive. TED, trailing edge down for the elevator, is positive. The IH, when it is going upward, it is positive. So aileron, elevator, rudder, and incidence angle of these things I have discussed. So it is very much essential for any student to understand what is the positive direction and what is the negative direction. Otherwise, during solving your problem, you will confuse that which side I have to take positive and which side I have to take the negative. So it is very much essential that the first thing is elevator. So if elevator is going down, it is a positive. Rudder, if it is going towards the left, so if it is going the left, nose will also go left. So if nose is going towards the left, it is a positive. And rolling, if left is going down, means right wing will go down. So if right wing is going down, it is a positive aileron deflection. So these are the direction for the. Now example of control moment. For a positive elevator deflection, that is delta E, will typically results in a negative nose down pitching moment. Okay, so this thing is very much important. You have to understand that when the positive deflection of elevator means if it is going down, okay, then what will happen? If it is the going down, the lift of horizontal tail will be up more. More lift will be generated, and this more lift will try to make nose down. So the positive elevator deflection will make the nose down pitching moment. Okay, so this you have to understand that positive elevator deflection will make nose down. A positive IH will also make nose down. So if we want to make the longitudinal stable aircraft, then we have to make this angle, the IH, the incidence angle of the horizontal tail, it should be little upward. If it is little upward, more lift will be there, and the tendency of aircraft will be the stable aircraft or nose down or negative pitching moment. A positive aileron deflection delta A will typically results in a positive right wing down. Okay, so if delta A is positive, I told you, it means the left side aileron is going down. If the left side aileron, this one is going down, lift will be more and the right wing will go down. So delta A positive means what? Right wing is going down. The rolling is towards the right side. Then we can say that it is a positive aileron deflection. A positive rudder deflection, delta R, will typically results in a negative or nose left. So if it is going left, so lift will be this side more, nose will go like this. So lift here is more, it is pulling like this, nose will go like this. Okay, so the yawing moment, opposite sides are negative. Okay, so these are the all four conditions which I have already explained you people, and hope it is understood to one and all. And it is very much essential to understand the concept of positive and negative control deflection. Now we have to we can follow the right thumb rule for finding the positive or the negative moment. So if you see here, if the right thumb is placed along the elevator, okay, just you see here, this is the elevator. So if I place my this elevator in the line pointing in the direction of the positive y-axis, so this is the positive y-axis, so I have to put like this, the finger curl in the leading edge down. Okay, so just you can see it is like this. Such is defined as a positive. So if this is the y direction positive, so if you put your hand like this, your fingers are down. So if your fingers are down, then it is a positive elevator deflection. For a rudder, the thumb is pointed towards the direction of the z-axis out of the bottom of the. If I am putting like this, and the finger curl in the trailing edge left direction. Okay, so it is like this. Then we can say that it is a positive. So it is in this direction and your rudder is going in this direction. We can say that the aircraft is in positive direction. Okay. So in this way, we can decide all these parameters. Now the cross control derivative, the next one is CL delta R and CN delta A are called the cross control derivatives because they define the change in moment that results from the change in a control surface. That is not the primary control surface for that axis. Okay, so you can see here very interesting issues. Cross. Previously we have seen the control power, and in this you can see here that Cm delta E. The Cm is depend on the elevator. Now CL delta I, this rolling moment is happening with the aileron. Here Cn delta R, this Cn delta R is happening due to the rudder deflection. But when we talk about the cross control derivative, if it is the cross control derivative, so you see here CL is a coefficient of rolling moment due to the deflection of the rudder, and Cn delta A, it is a coefficient of yawing moment due to the aileron deflection, are called the cross control derivatives because they define the change in moment that results from the change in a control surface that is not the primary control surface of that axis. Here, example, CL delta R defines the change in rolling moment that results from a change in a rudder deflection. Okay, so how it is happening? CL delta R means rolling is happening due to the deflection of the rudder. And how it is happening? Just we can see here that aircraft is flying like this. You have changed the rudder. So if you change the rudder, suppose you are changing towards the left. So nose will go towards the left. So if the nose will go towards the left, the right wing will have the more velocity. Okay, so if it is going like this and it is turning like this, this will face relatively less relative velocity than this. The right wing will feel more relative velocity. So in the right wing, you will have the more lift. This lift, the right wing, the lift will be more than the left wing. So there will be a roll also. So you are turning the aircraft by the help of the rudder, but due to this delta R deflection, there is a rolling moment, and this rolling moment is negative. Okay, because it is left is going down. If right is going down, it is a positive. So it is a negative rolling moment. So like this, we have to understand. So this is called the cross control derivative. It means it is not related, the deflection of the control is not a primary control. Like rudder, the purpose of rudder is to turning the nose towards the left and right. But it is turning and also it is rolling also. So that is the objective of understanding the cross derivative. So with aileron being the primary control surface of the roll axis. So here the CL, the aileron should be applied, but without application of aileron, once we apply the rudder, this will take place and it is happening in same way. Next is the CL. So it is actually not CL, it is a CN. Defines the rolling moment that can be generated with a non-primary control surfaces or the rudder. Okay, so we have to understand that what is the CN. So here you can see that the sign convention, the primary control derivative have the following sign. Cm delta E is negative, CL delta A is a positive, and Cn delta R is negative. Okay, so this we have to understand. And here CL delta R and Cn delta R, I have just now explained how these things are happening and how we are going to handle this Cn delta R and Cn delta E. So for the Cn delta A, Cn delta A is what? It is a yawing moment coefficient when we vary the aileron. Normally the function of the aileron is what? The function of aileron is to make the rolling. It means what? If I want to make right wing down, the aileron of the left wing will go down. Here you will get the more lift. Here you will get the less lift because this aileron is going up and this aileron is going down. So the right wing will face less lift. The left wing will face more lift, aircraft will roll right down. Once it is rolling right down, then what will happen? Whether it will yaw or not. So if it is rolling right like this, then what will happen? This side, the induced drag of this side and the induced drag, because this lift is high this side. So in this side, there will be a more lift, and here in this direction, there is more drag comparing to this. So there is a chances of this will go towards the left. So being rolling, during rolling, due to the difference in the lift in the both the side, the right wing will have less drag, induced drag, than the left wing. Left will have the more drag. So this will be pushing like this. So this is called Cn delta A. That is why they are the cross coupled. Normally in the longitudinal axis, when we study, we don't consider the coupling with rudder and the aileron. Elevators are independent. They are not disturbed by other control. But in yawing and in rolling, both are the interlinked. If you are rolling the aircraft, yaw will happen. If you are yawing the aircraft, roll will happen. And that is why the cross control derivatives are coming in the picture. That is why we have to understand this basic concept of cross control derivatives. If you understand the basic concept, it will be very easy to understand all these topics, which will be useful for understanding the real stability problem of the aircraft. So I have referred in this some textbooks. I appreciate the Yachout TR et al. That is the Introduction to Aircraft Flight Mechanics. Very good concept in this book. And you can understand very well, very, very nicely explained each topics. However, the Nelson RC also a good book, especially for the numericals and all. It is very nicely explained. Further reading you can do by the NPTEL lecture of Aircraft Stability and Control by Professor A.K. Ghosh from IIT Kanpur, and this will be very useful for all the students, and very nice courses are there, online courses in the Swayam platform. So it will be very nice to read these books and try to understand the concept of aircraft stability and control. So I am thanking you for all for joining this class. Hope this will be very interesting and very thoughtful for about the aircraft stability and control, and it will be really very interesting to understand the concept. So just I will revisit all the today I have discussed. I have discussed about the starting point. I will go here, and this you can see here that I have gone for this stability, then stability derivative, then the sign, then the criteria of longitudinal static stability. In this, Cm delta A was very important. So the Cm delta A should be negative, and dCm by d alpha should be negative, and Cm naught should be positive. So this is the first criteria. We have to meet these two criteria, that is dCm by d alpha less than 0 and Cm naught should be greater than 0. If we are able to meet this two criteria, we can fulfill the criteria for longitudinal static stability. Then we have learned the primary control derivatives, the effect of the elevator deflection, effect of the this horizontal tail setting, and this all things, effect of rudder, effect of aileron deflection on the different types of this coefficient of moments and other things. And sign convention also. So if trailing is going down, it is a positive. If incidence nose leading edge is going upward, that is called leading edge upward, it is a positive. And for the aileron, if delta A should be positive, and for TEL, trailing edge left, it is a positive. And also I have given this example, and so I would like to cross control derivative. I would discuss about this, that how this, if you change the rolling, pitching will, if you roll the aircraft, yawing will happen, and if you yaw the aircraft, roll will happen. Both are the cross coupled, and I have this thing. Okay, thank you very much for joining this class, and hope you all have understood very well.
Like, share and subscribe. Hit the bell icon for more updates.